My name is Akil Bavia. I'm a senior at Johns Creek High School.
I'm Anshul Visnell, also senior at Johns Creek.
I'm Alexander Hammond, also senior at Johns Creek.
I'm Dean Wang, also senior.
I'm Danny Burdett, also senior.
And we're team number 9120.
I'm Kara Bliss. I'm an assistant professor at Virginia Military Institute.
I'm Dan Connors. I'm a research staff member at IBM Research.
I'm Kelly Black. I'm at the University of Georgia in the department.
Amanda Babson. I'm the Coastal Climate Adaptation Coordinator with the Northeast Region of the National Park Service.
Chris Bergman. I'm an associate analyst with Moody's Investor Service.
So you'll have 15 minutes for your presentation. When there's 2 minutes left, I'll signal you so that you'll know that we're getting close on time. After that, we'll ask you a few questions and then you're done. So please go ahead and get started.
Hello everyone, we're team number 9120 from Johns Creek, Georgia. We're really excited to be here today to share our solution with you. Over the last 50 years, average global temperatures have increased at the fastest rate in recorded history. This phenomenon that we know as anthropogenic global warming has caused a variety of damaging environmental effects. In response to the threat of these global climate changes, the National Park Service, or the NPS, is taking steps to gauge the potential risks that our national parks face. So in order to help the National Park Service face these changes, we first created a conical model to determine the severity of sea level changes for 5 different national parks. In part 2, we then broadened our consideration to create an overall vulnerability scale that took into account 3 main factors: hurricanes, wildfires, and flooding. In part 3, in this final part, we use this vulnerability scale to develop a model that establishes investment levels for these NPS park units based on visitation data and the models that we have created in the past. With these models, we believe we've created a way for the National Park Service to prepare for these climate changes and to continue the preservation of these sites in the future. Now here's Anshul Visnell with more details about part 1.
Hi, I'm Anshul, and I'll be talking to you about part 1, where we were asked to determine sea level change risk ratings of low, medium, and high for the 5 national parks after 10, 20, and 50 years respectively. So first, to start our model, we made some simplifying assumptions. The first assumption was that the mean sea level trends, the MSL trends, for the 5 national parks were each assigned a constant value. This was because the monthly MSL data we were provided didn't seem to show any upwards trends in MSL values. Our second assumption was that each park is the same intrinsic value. That is, all the parks are, no one park is more important than another. That way they can be compared to each other directly. And our third and final assumption is that the area of each national park could be approximated by a uniform right circular cone with base equal to the total acreage of the park and height equal to the height of the highest peak of the park. We first thought of using the right circular cone when we were looking at topographic maps of the parks. So as you can see from the map of Olympic National Park, for example, it follows the general trend that the highest peaks are in the center and the areas around the shoreline are lowest in elevation, kind of like in a cone. So the conical model we formed has 3 main parts. To the equation. The first part is the proportion P that gives the proportion of the park bordering the ocean as a function of the shoreline length of the park, L, that you can see from the diagram, and the acreage of the park, AB, which is the bottom circle in that line. The second part of the equation is the initial surface area of the cone, which is the surface area of the park before sea level rise occurs, given just by the surface area of the cone. And the third part of the equation is the final surface area of the cone. That is the surface area of the park after sea level rise has occurred, given as a function of h of t, which you can see from the diagram, is the change in sea level based on the MSL trend at the park and the time. So putting these all together, we get the ratio of RD equals PAD over AI, where AD is the area destroyed, given by the initial surface area of the park minus the final surface area of the park. And when we applied this model to the 5 parks after at 3 time periods, we obtained these values for RD, the ratio of the park destroyed. As you can see, the most mountainous parks, Acadia and Olympic National Parks, had relatively lower percentages destroyed than Cape Hatteras and Padre National Seashores, which are flatter parks, which intuitively makes sense. And Kenai Fjord's values were negative because MSL trends there are decreasing, opposing the global norms. To objectively determine the risk level classifications of low, medium, and high, we looked at U.S. flood damage's proportion of GDP. As you can see from the graph, the lowest flood damage as a proportion of GDP was 0.05% in 2012, and the highest ever recorded was 0.75% in 1951. So we determined low risk to be anything that damaged less than 0.05% of the park, anything between 0.05% and 0.75% would be medium risk, and anything above 0.75% would be high risk. And using those risk level classifications, using that scale, we obtained these risk level classifications based on the RD values obtained previously. So now Alex Hammond will talk to you a little bit about environmental prevention.
For part two, we come up with a climate vulnerability index based on the likelihood and severity of climate-related events that occur in the park over the next 50 years. Our first assumption was that only sea level change, wildfires, and hurricanes would do significant enough damage to the park for us to include it in the model. Any other changes or any climate-related events we felt either did not have enough data about them for us to include in the model, or there was not enough data showing a correlation between that event and the climate for us to include. Our second and third assumptions were that wildfire damage would be constant within the class of wildfire, and hurricane damage would be constant within categories of hurricanes. And we felt that this assumption was justified based on the law of large numbers, whereby all the damage would regress to the mean over the period of time that we're looking at. And we calculated the damage that each of these classes and categories would do based on data provided to us in the problem, as well as data calculated from the National Oceanic and Atmospheric Administration's data about Hurricane Arthur's impact on one of the parts included in the study. Our general model was calculating the risk based on the severity of damage times the likelihood of that damage occurring. We used this equation multiple times to calculate risk for each of the individual functions that we developed. So in our overall model, we split up into 3 different functions, one for each of the natural disasters that would occur, so one for flooding, one for wildfires, and one for hurricanes, where by each of these functions we calculate the damage or the risk to a national park based on the number of years over which we're doing it, as well as the factors included that were park specific. To develop the flood model, we had the damage done from our part 1 data, so we had to multiply it by the probability of that damage occurring. In order to do this, we created this distribution of all the MSL data gathered by the National Park, or gathered by NOAA from 142 different tide stations, and created this Gaussian distribution, which we integrated to plot a combined density function. And then using integrals of this function, we were able to calculate the likelihood of the given MSL values provided by the National Park Service of actually occurring. And we also assumed here that the MSL values that they provided to us with 95% confidence interval would be the MSL values that actually occur. We didn't feel that we needed to include any outliers beyond this, but within the remaining 5%, because over the 50-year time period, they wouldn't have that significant impact. So this is the final equation we came up with for our weighting factor, and you can see at the end we multiplied by the damage done, calculated in part 1, which is the L times AD over 2 square root pi AD, using the same constants that Marshall just explained for you. But yeah, this is our weighting factor, which calculates the probability of the given MSL value for a park actually occurring. For developing our wildfire model, we felt that the best way to plot the effect of climate change would be to see how wildfires would change on a national level, since anything park specific was not a clear enough trend for us to track. And so we plotted this regression, which we felt followed a very clear visual trend, although the data oscillates enough that it threw off the R-squared value. Using this regression, we were able to calculate the amount of wildfire damage that there would be in a given year. And by integrating it over a 50-year period, we were able to approximate the amount of damage that occurred nationally over a 50-year period. And then to make it park specific, we multiplied by this constant because we felt that the proportion of damage done to the park over the last 20 years relative to the amount of damage done to the U.S. over the last 20 years would hold constant over the next 50 years, so that the amount of damage over the next 50 years done to the U.S. would be proportional to the amount of damage done to the park in the next 50 years. So you can see we multiply the constant by the total amount of fire damage to come up with the expected damage within the national park over the next 50 years. For hurricanes, we similarly felt that plotting it nationally would be more representative of the impact of climate than plotting anything locally. And so we came up with this overall trend of hurricanes. We saw a slight increase in the number of hurricanes over time, and so we found a linear regression that represented this. And using that, we were able to integrate to figure out the number of hurricanes over a given number of years X, as you can see. and we similarly multiplied by a proportion of the number of hurricanes of a specific category that hit the park since 1995 over the total number of hurricanes since 1995. By doing it by category, we could then multiply by the category constants you see down here, which is the percent of the park that would be destroyed by that category of hurricane. Then we summed all 5 different categories of hurricanes to figure out the approximate damage done by hurricanes to that park over a given year. And then we integrated over a 50-year time period to figure out the total amount of damage done by hurricanes to a national park. So then we combine all of this into our overall model, which you can see here. This is just the 3 functions all added together, using all the different park-specific values to come up with the overall damage. That damage, E total, we then divided by the surface area total of the park to come up with the vulnerability index, which we considered the percentage of the park that would likely be destroyed over the next 50 years. This allowed us to easily compare the percent of the park that would be destroyed, you can see down here. And it showed that hurricanes were huge factors. As you can see, the most damage is in Padre National Seashore because of its significant hurricane damage. And then below that, flooding due to sea level rise was a significant factor. However, wildfires we found had very little impact on the overall damage done to the park over the next 50 years. So with part 3, here is Jamie White.
Hi, my name is Jamie Wang, and I'll be going with part 3, which deals with future investment and funding allocation for each of the national parks as a result of climate change. And so, in order to develop a model for part 3, what we first had to do was take into consideration which factors would be influential for creating the model. Just from government knowledge, we figured that the most important factors in determining a park budget would be management, operations, facilities, visitation needs, and future funding. For the first 3, we ended up bundling them into fixed costs, which were not taken into consideration because those don't change as a result of climate change, and therefore only visitation needs and future planning as a result of climate change are taken into account as well. So in order to get the changes in the number of visitors as a result of climate change, we took the data that was provided to us from the NPS and plotted linear regression lines to find an equation that would predict the overall trend. Using that line, we then integrated over the next 50 years to calculate the total number of visitors who would be visiting each park. And then we then took the total number of visitors and multiplied it by the vulnerability index that we calculated in part 2. This creates a new variable called key park. And key park, it may seem arbitrary at first, but key park is actually the risk determining factor of funds. And it's essentially the magnitude of the impact, the vulnerability index that is, multiplied by how many people it affects, which is the total number of visitors. And to standardize each park's key park to get a percentage of funding allocated, we took each park's individual value and divided it by the sum to get a proportion. And we then use that proportion as a proportion of funds allocated, with Padre and Cape Hatteras receiving the most funding, followed by Olympic and Acadia, and Kenai Fjords with 0. And I'll pass it on to Dana for data for part for strengthening the use of the model.
So, we see several opportunities to improve the model in geometric assumptions, damage considerations, and forecasting. First, geometric assumptions. In part 1, we assume that every park is a right circular cone. However, some parks may be regular shapes that largely deviate from cones. We have to make this assumption to standardize surface area and to make calculating damage feasible. Second, damage considerations. In part 2, we assume that only damage from flooding, wildfires, and hurricanes actually affected the park. Our model doesn't factor in other disasters like earthquakes or mudslides due to insufficient data. Last, forecasting. We assume that past trends are predictive of future trends because the regressions take the past dozen years into account, where most climate change has happened. However, our correlation coefficients were lower than we would have liked because we were not able to investigate different stratifications in the data due to time constraints. Now, with that, our model also has many strengths, as it is empirically derived, intuitive, and dynamic. First, empirically derived. All constants and regressions are based off of comprehensive real-world data and an understanding that climate change will actually exacerbate disasters.
So our model is consistent with past trends and is predictably valid. Second, we have intuitive results. For example, Kenai Fjords National Park has negative sea level trends. So our model takes that into account and shows that it's actually gaining land, which is consistent with recent Alaskan Daily News releases. Additionally, all of the parks used in testing the model are coastal national parks. So it makes sense that wildfires do less damage as opposed to water-based disasters like flooding or hurricanes due to their proximity to water. And that's all consistent with each section of Part 2. Finally, and most importantly, our model is dynamic. And when we say dynamic, we mean it twofold. First, the hurricane values are constantly changing. In Part 2, we incorporate a hurricane average that constantly builds upon the previous years and correcting it, and it self-corrects itself and is a more consistent value than just a generic average that we determined arbitrarily. Second, cross-park applicability. If we know the acreage and peak height of any national park, and we have empirical data on wildfires and hurricanes within that national park, then we can determine the total damage that that park will sustain. In conclusion, given our simplifying assumptions, we have created a model that is empirically sound, has intuitive results, dynamically builds upon itself, and can be applied to any national coastal park over any number of years and still provide values consistent with what we'd expect. And so we're excited to be here in front of you and present our work today. We'd like to thank our coach, Ms. Mir, for being an inspiration, and she's just been an amazing teacher over the years. We'd like to thank Anirudh Suresh for being an amazing mentor and providing feedback for our presentation. We'd like to thank the National Park Service for preserving our parks. And we'd like to thank Moody's and SIAM for this wonderful opportunity, having us here today, and giving us the opportunity to display our passion for math in a means that's potentially beneficial to society. Thank you.
Can you bring up page 25?
Yep.
Okay, we had trouble understanding when we read the paper and even seeing here, there are a lot of x's floating around there. And you got f of x dx integral from 0 to x over x. Can you explain that term?
Yeah, so what that's doing is summing the overall hurricane damage that there's going to be in the next 50 years based on f of x, and then dividing.
So what f of x is?
So f of x is the hurricane damage within a year.
Okay.
And then we're integrating that over the number of years x, and then dividing by x to figure out the average number of hurricanes up to that point in history, because we felt a moving average would be a little bit more accurate by accounting for any outlying years, since we saw some years would have like 20 hurricanes versus some years would have 0. And so we felt that a moving average would be more representative of the data than just the evaluation of the function f of x. Does that make sense? And so then we used that average as our total number of hurricanes in a given year, or in like the year that we're evaluating at, and then we multiplied that by our constant, by the constant of the number of hurricanes in a specific category over the total number of hurricanes, multiplying then by the damage done by the category of hurricane, then by the surface area of the park, to come up with the overall amount of damage done by that type of category of hurricane to the park within a given year. Then we summed you can see the sum is for each of the 5 categories of hurricane, sorry, and then we integrated that over 50 years. So we basically try to calculate the amount of damage done by hurricanes overall within a given year, and then integrate by 50 years. As we felt integrating earlier on, we would have some issues with adding the damage done by different categories of hurricanes.
Okay, thank you.
So on page 15, the value of beta for Acadia is on the order of 10 to the minus 5, and the value for Olympic is on the order of 10 to the minus 7. How do these numbers compare to each other and the others, and how do you interpret your calculations of these values? What do they mean?
So each of the values with beta are proportions for how much of the damage we can expect that part to sustain.
It's page 15 of this.
Of the paper, sorry.
Yeah. So for our risk evaluation, we did the amount of the park that we expect to be destroyed over the total surface area of the park. So that really shows into the fact that for Acadia and Olympic, the amount of wildfire damage is minimal relative to the total surface area of the park itself. And then they suffer no hurricane damage because there haven't been any hurricanes in there in the data we gathered. And the sea level rise the sea level damage done multiplied by our weighting factor, which is the likelihood of that damage occurring, was so small that the amount of the park that's actually supposed to be destroyed, according to our model, is minuscule, which is why it's such a small number.
Your weighting factor is based on the percentage of the park destroyed under your chemical model, correct? Does that take into account flooding that's not directly due to sea level increases?
It does not. Given the time frame that the 14 hours we were given, we decided that we had to cut some losses when we were calculating our model. And so we felt that just taking the CDF level no data would be enough of an accurate representation of what would happen, because most of the flooding would occur due to its proximity to the ocean.
I have a couple questions here. On page 12, you refer to the NHS data. What is that referring to?
Page 12. Oh, the NHS data, which for the 95% confidence interval?
Yeah.
Yes. Yeah, that was data given to us in the problem set.
So that's NPS.
Yeah.
Okay.
Sorry.
All right, that's fine. Now you refer to the 95% confidence interval. What is that, and how are you using that?
Okay, so the data we provided on the original challenge problem gave us the trends in the millimeters per year for each national park. And so there was a 95% confidence interval in one of the Excel pages. That was the likelihood that the millimeter per year trend of sea level rises would fall within that category. So we assumed that that would be held constant and that it would fall within that category, or it wouldn't be considered to simplify the model. And so that interval is essentially just 95% confidence interval of what we've seen in the national parks mean sea levels be in the past. And we felt that was an accurate representation of the weighting factor.
Thank you very much.